We're around electricity literally every second of our lives, right? But what is it, really? We know we flip a switch and a light comes on, but underneath that simple action, there are these incredible hidden forces at play. Fundamental principles of heat and motion that actually shape our entire world. So in this explainer, we're going to pull back the curtain and uncover those secrets.
So let's ask that question directly. Beyond just making things glow, what can an electric current truly accomplish? Well, it turns out it has these two secret powers that, and I'm not exaggerating, underpin almost all of our modern technology. The power to create intense heat and the power to create an invisible, moving force.
So here's our game plan. We'll start with the basics, how electricity even carries energy. Then we'll dive into its first power, creating heat. After that, we'll explore its second, more mysterious power, magnetism. We'll see how that magnetism creates motion in electric motors, and then we're going to flip the whole idea on its head and ask, can motion also create electricity?
All right, Section 1. Electricity's hidden powers. Before we can get to the cool stuff like heat or motion, we first need to get a handle on how electricity actually delivers energy in the first place.
You know, the best way to think about it is like a delivery service. You've got a source, say a battery. That's the warehouse providing the energy. The electric charge, that's the delivery truck flowing through the wires. It carries that energy package and delivers it to a component, which then transforms that electrical energy into something else entirely. Heat, light, or even motion.
Okay, Section 2. The power of heat. This first transformation is probably the one that makes the most sense to us, turning that electrical flow into a warm and sometimes very bright glow.
So why does this happen? Well, as a current of electricity flows through a material, it bumps into stuff. It encounters resistance. You can almost think of it as electrical friction. And that friction converts the electrical energy directly into heat. It's a fundamental principle called Joule's law, and we use it all the time.
And once you know about it, you see this effect everywhere. Your toaster, it uses special coils of a material called Nichrome that has a super high resistance to get hot and brown your bread. That old school incandescent light bulb, it heats a tiny tungsten wire to an incredible 3,400 degrees Celsius until it literally glows white hot. We even use this for safety. A fuse is really just a special wire designed to get hot and melt, breaking the circuit if the current gets dangerously high.
Section 3. The power of magnetism. So, heat is one power, but electricity has a second, much more mysterious one, an invisible force. And this is where things start to feel a little bit like magic.
You know, for the longest time, people thought electricity and magnetism were two completely separate forces in the universe. But that all changed back in 1820. A scientist named Hans Christian Ørsted was doing a demonstration, and he noticed that when he passed an electric current through a wire, the needle on a compass nearby twitched. He was the first to prove they were deeply, deeply connected. An electric current creates its own magnetic field.
And what's really cool is we can even predict the direction of this invisible magnetic field using a really simple trick. It's called the right-hand thumb rule. If you just imagine grabbing a wire with your right hand, and you point your thumb in the same direction the current is flowing, the way your fingers curl around that wire shows you the exact direction of the magnetic field lines. Simple, but incredibly powerful.
All right, Section 4. How electric motors spin. So a current creates a magnetic field. That leads to a really fascinating question. What do you think happens if you put that current-carrying wire with its own little magnetic field inside another, bigger magnetic field? The answer is the two magnetic fields interact. They push and pull on each other, and that creates a real physical force. A push. This right here, this is the secret to creating motion from electricity.
And just like before, there's a handy rule to figure out which way that push is going to go. It's called Fleming's left-hand rule. If you know the direction of the magnetic F and you know the direction of the current, this rule tells you the exact direction of the resulting force, the motion. This one principle is the absolute heart of every single electric motor on the planet. A motor is just a clever device that takes this simple push and harnesses it. By shaping the wire into a loop, it turns that little nudge into continuous spinning mechanical energy. And one invention, oh man, it changed everything. The electric motor is the unsung hero of our daily lives. It's spinning in your fan, it's in the compressor that keeps your refrigerator cold, it's in your washing machine, the hard drive in your computer, your kitchen mixer. The list is practically endless. They all work because a current in a magnetic field creates motion.
Okay, Section 5. Making electricity from magnets.
Now we get to what I think is the most elegant and beautiful part of this whole story. See, physics loves symmetry. So if electricity plus a magnet can create motion, does that mean motion plus a magnet can create electricity?
This is the very question that obsessed the brilliant scientist Michael Faraday. He reasoned that if an electric current could produce a magnetic field, then maybe, just maybe, the reverse was also true. Maybe a moving magnetic field could produce an electric current.
And in 1831, he proved it. He discovered what we now call electromagnetic induction. The secret he found is that the magnetic field has to be changing. If you move a magnet near a coil of wire, or you move a coil of wire through a magnetic field, you induce a current. You literally create electricity out of thin air, using motion.
And yep, you guessed it, there's a rule for this too, and it's the perfect mirror image of the other one. For this, you use Fleming's right-hand rule. If you know the direction of the motion and the magnetic field, it'll tell you the direction of the induced current.
Section 6. Generating our electrical world. This is the grand finale. This is where it all comes together. Because that single principle, electromagnetic induction, is how we generate virtually all of the electricity that powers our civilization.
So let's just put it all together side by side. An electric motor takes electrical energy and turns it into mechanical energy, motion, governed by the left-hand rule. An electric generator does the exact opposite. It takes mechanical energy, motion, and turns it into electrical energy, governed by the right-hand rule. They are two perfect sides of the same incredible coin.
Now, there's one last interesting detail. The current that these generators produce isn't like the steady, one-way flow you get from a battery. That's called direct current, or DC. Instead, as the coil inside the generator rotates, the induced current naturally flips its direction every single half turn. This is called alternating current, or AC, and that's what comes out of the sockets in your wall.
In many parts of the world, including India, the standard frequency for this AC power is 50 Hz. So what does that actually mean? It means the current flowing into your devices, into your lights, your computer, it is completely changing its direction back and forth 50 times every single second. It's happening so incredibly fast we don't even notice it.
So there you have it. From the simple warmth of a wire to the spinning motors in our homes and the giant generators that power our entire world, it all comes down to this beautiful, inseparable link between electricity and magnetism. They aren't two things, they're two aspects of a single force, electromagnetism. Which leaves us with one final big thought. What other fundamental forces in our universe are just waiting to be revealed as two sides of the same coin?